This is a very qualitative presentation. Before I get into it, I need to again mention that we'd be delighted to receive your questions. I see there was a question about a problem with user interface, and that's something I think we'll have to pick up after the course. Okay, with regard to computational modeling and the numerical methods underlying that, the purpose of my presentation is to give a qualitative introduction that I hope will help you understand some of what's going on. So here we have at the top, a cartoon of a section that is chopped into several segments. And notice this is a part of a section, even though it's got, it has an even number of segments being shown. We're not endorsing the use of an even value for nseg. In fact, we advise against that because there is no node in the middle, and anything you do that creates new nodes, like multiplying nseg by 3, is going to cause you problems at this point. But in any case, this cartoon is meant to suggest the nodes at the middle of the segments. And if you'll see the axial resistors in the schematic diagram just beneath the cartoon, you'll see that between adjacent nodes, there is a resistor. And to the left of the leftmost node and to the right of the rightmost node, you'll see a half of a resistor. So that's what you would expect. The equivalent circuit of an individual compartment would be 1/2 of one of these axial resistances on the left and another half of the axial resistance on the right of this parallel combination of membrane capacitance and this little white box which contains all of the ionic conductance representations that are in a given segment, okay? And this is what you get when you create a section, only without with nothing in these white boxes, okay? Because you just get the axial resistance and the membrane capacitance. If you insert mechanisms like pass, HH, you get other things inside these little white boxes. All right. If you insert, okay, so there's one ordinary differential equation then for each node for the cable equation. And then there's as many differential equations as well for each node as are required to take care of the gating properties that are inside these little white boxes. Now, if you add the extracellular to a section, what you get is a second layer consisting of, first of all, a longitudinal external resistance between these longitudinal nodes that are on the representing potential at the outer surface of each segment. And then you get a parallel resistor capacitor combination and a battery in series with that, which is then connected to ground. Okay, so the extracellular barrier can be used to represent myelin, that is to say radial, that is myelin electrical effect for radial current spread, and these longitudinal resistors in the Vx layer represent the longitudinal resistance in that immediate gap right next to the membrane between the myelin and the membrane. And of course, those longitudinal resistors would have a very high value. Okay. So, what is NEURON doing when it solves the first order differential equations that we throw at it? Well, let's take a look at some of the methods that could be used to solve a first-order differential equation. So this diagram we'll start by looking at the equation up in the upper right corner. The general form of the equation is the first derivative of y is some function of y. And the simplest form that gives a stable solution analytically is our old friend derivative of y is equal to minus y. And we know the analytical solution to that. And if our initial condition is that y is 1 when t equals 0, then the solution is y equals e to the minus t. Okay? So what this figure shows is that actually this differential equation defines a vector field, if you like. And by vector field, I mean that at every point in this plane, points to the right-hand side of the origin represents, the vertical line passing through the origin represents time equals 0. All the points to the right of this represent potential solution points during a neuron simulation, okay? And at any point in this right hemiplane, the slope at that point is equal to minus 1 times the y coordinate for that point. So the farther you get away from the x-axis, the steeper the plots become, either in a negative direction or in a positive direction. And any solution is going to be tangent to elements in this vector field. Okay, so any analytical solution is going to pass tangent locally to the slope in this vector field. Okay, so this suggests a simple way, a simplistic way of trying to numerically compute a solution to this differential equation. And the simple way is the forward Euler method, which works like this. If you're at a particular point, you calculate the slope at that point, and you follow that slope toward positive times. And you follow that slope by an amount of time that is equal to your time step. Okay? And if you do that, that becomes the next point where you try to advance the solution. So we start out with an initial condition of y equals 1. The slope here is minus 1. We move along that slope for a half a millisecond. At this point, we find that y value is 0.5 and the slope there is minus 0.5. So our next solution step will take us from here to here with a slope of 0.5. And then our next solution point is along the slope of the vector field at this point in the field, okay? All right. So you'll see here then a solution to this differential equation with a time step of 0.5 milliseconds. And the numerical solution is always approximate. But in the end, it converged on 0, which is where the analytical solution is going anyway. So that seems okay, not too bad. If we make smaller and smaller time steps, we'll get solutions that are more and more accurate. We'll go less far before we calculate the slope, and we'll have less error. But what happens if we are trying to achieve some computational speed? Suppose we have a model here where we have two compartments. Each one has its own local time constant of 1 millisecond, and their intracellular nodes are connected by a resistor whose value is 1/20th of the membrane resistance. Okay? Well, this introduces another time constant into the solution. The solution is no longer a mono-exponential. There are now two time constants. One time constant is fast, and it takes care of equilibration between this node, where V1 is measured, and where V2 is measured. And the other time constant is slow, and that takes care of the decay of these two membrane potentials towards zero. So if we start with an initial condition of, say, V1 having a value of 2 and V2 having a value of 0, okay, there's the one initial condition for V1 and there's the initial condition for V2. The first thing that happens is the dynamics are dominated by equilibration of membrane potential between these two nodes, okay, so that they become more the membrane potentials here become more approximately equal. So they collapse toward each other very quickly. And this is a very steep slope. So we take a small time step, 0.02 milliseconds. And this is our approximate solution. You'll notice that it undershoots the analytical solution slightly. This is the analytical solution. Actually, this is a numerical solution as well, but with a much smaller time step. So if we continue, we see the two potentials collapse toward each other, and then they start to decay slowly. Now, if we wanted to achieve some computational efficiency, we might think, well, things are moving very, very fast here, so we needed a fast time step. But when they start to move very slowly, maybe we can get along with a longer time step. So let's make dt be 0.2 of a millisecond, 10 times longer. Okay? And so now our solution can zip along much more quickly, except that we eventually start to see oscillations in the solution. And the oscillations are getting bigger and bigger at every new step until we get these massive overshoots and the solution blows up. Well, what's going on here is that we're using this forward Euler method to solve a set of equations in which the fastest time constant is much smaller than our time step. Okay? What is the slowest time constant is obviously 1 millisecond. The fastest time constant is closer to 1/20th times 0.5, which is the series equivalent of 1 and 1. Okay? 1/20th times 0.5 is 1/40th. So our fastest time constant is 1/40th of a millisecond, but we're taking time steps which are much larger. Okay, 1/40th is 0.025. So we're taking time steps that are about 8 times larger, and that's why we get this blowing up. That's what happens with the explicit or forward Euler when your time step is larger than the system time constant, than the smallest system time constant. And the problem, of course, with all cable models is that the membrane time constant is always much longer than the equilibration time constant between adjacent compartments. That's just the way it is. If you've got adequate spatial discretization to get decent spatial accuracy, you're going to have very fast longitudinal equilibration, much faster than your membrane time constant. So forward Euler, and God help you if you've really got some tiny short compartments like a spine neck. So forward Euler is not a real good idea unless you want to wait a very long time while you're using many, many, many tiny simulation steps. Better than that is the backward Euler method. What does the backward Euler method do? Instead of using the local slope in the vector field, what it does is it looks, when you start at some initial condition, it looks a time step ahead in the future, and it tries to find the y value where the slope there points back at the point that you're coming from. So forward Euler looks forward from where you're starting. Backward Euler tries to find the step in the future where you're looking back at the point you came from. And backward Euler lags a bit behind the analytical solution, but it's always stable. It also is a bit more complicated to solve. because we have to solve this equation, okay? That requires an evaluation of this function at future values. That essentially requires matrix inversion if we're talking about linear equations, okay? Or linearizable equations, okay? And that's computationally more expensive, but it is unconditionally stable, okay? And it's always gives you a nice value no matter how far in the future you go. This dashed line is the locus of values that you get depending, plotted versus the time step. So if we did a time step of 3 milliseconds, we'd end up at this point because the slope at this point points back to here. And that ain't too horrible. Yes, it is. The error is bad, but if we go out further in the future, it never blows up, and it always at infinite time reaches the same steady point, the same stable point as the analytical solution does. Okay? So the implicit Euler or backward Euler is stable, and that's why that is NEURON's default method. It's cheap, relatively compared to other methods. It's more expensive than forward Euler, but at least it's stable. Okay, and in fact, the error when you're using like a 0.025 millisecond time step, the error isn't too bad when you consider the inaccuracy of our parameters that we're basing our models on. I mean, we don't really know diameters to, high precision, especially not when you get down to 1 micron diameter neurites, where most of the area of most real cells is. And we don't even know if those cross sections are circular. They might not be. They probably aren't. So the assumption that your cell that you've reconstructed has circular cross section of its neurites, I'm sorry, it ain't so. So there's a lot of errors, not to mention the biophysical parameters, what errors there are in those time constants and channel densities. So backward Euler is a little sloppy, but it's good enough for most purposes. So we can see that backward Euler is indeed stable when we go back to this model and we use a long dt for the entire solution. And we see that the solution is kind of qualitatively similar to the analytical solution. We get this initial rapid change as the two potentials of these two membrane potentials approach each other quickly, and then it converges on a value where they're very close to each other, and then we get the mono-exponential decay, where both nodes are falling towards zero. And we can do this variable time step thing without having a problem. We can use a short time step when things are changing rapidly, and then we can change it to a much larger time step when things are changing slowly, and we get a solution that is even qualitatively better than what we got with just using this huge time step. So backward Euler is pretty decent. Okay, NEURON also has something called the Crank-Nicolson method. And the way for the Crank-Nicolson method works is, instead of looking at the initial slope, where we're starting from, or trying to find the y value where the slope points back to where we came from, the Crank-Nicolson tries to find a point halfway through the time step where the slope points back to where we came from and uses that same slope to project to where we're going at the full time step. So if you like, this first part is a backward Euler step, and this second step is a forward Euler step, okay? But it's all accomplished easily and cheaply, okay? So because whatever increment we use to get from here to here, since the slope is the same, we use again the same increment of the y value to get from here to here. So we essentially do a backward Euler for half of the time step, and whatever that did to the value of y, we take an additional amount off of y and end up here. So that's very cheap, very inexpensive. and it does a much more accurate solution. Again, the solid trace here is the analytical solution, and you'll see how quickly it becomes very close. Okay, but you have to watch out, because if you take too long a time step, here's the locus of solution points as a function of dt. You'll notice that if you go too far, your solution points go to negative values. The solution is still stable in the sense that, yeah, you get oscillations and overshoot, but they die away with time. But the oscillations can be pretty big and pretty ugly. So you want to keep your time step short when rapid change is going on, and then you can change it to be longer when slow changes are going on, and you'll see the numerical solution and the analytical solution are really very close here. Okay? All right. NEURON has a Crank-Nicholson method that it can use. Okay? And it gives you better accuracy than the implicit Euler. Not as good as adaptive integration, which Robert's going to talk about. Adaptive integration, I'm going to mention this here, uses a set of algorithms that calculate how big a time step to change to use based on the local error at each advance. When it starts a solution, it takes a very small time step. It makes an estimate of local error. If the local error is smaller than a tolerance value that you set, you don't set the time step here. You set the error tolerance that's allowable. And these algorithms automatically change dt and the order of integration to try to keep the local error at or below this absolute tolerance. And you'll see what it does to the time steps and what it does to the solution. Very nice looking solution. Okay. If you can get a little bit of speed up if you relax the error tolerance, but watch out, because if you make the error tolerance too sloppy, you'll get bizarre stuff like these weird overshoots and peculiar oscillations. Okay? And if you start to see any of that instability looking stuff in your solutions, it means your error tolerance is too loose. You need to change it. Maybe you need to apply a tighter tolerance only to certain of the state variables. And Robert's presentation is going to address some of that. Okay? All right. So finally, we get down to practicalities. How do we use this in practical terms? Let's say we have a simple model, Hodgkin-Huxley single compartment. And we apply a nice, highly superthreshold stimulus. And we compare the solutions generated with 4 different methods. Crank-Nicholson with a dt of 0.001 milliseconds, that's a 1 microsecond time step. Crank-Nicholson with a dt of 25 microseconds. Adaptive integration with an error tolerance of 0.01. 0.01. And plain old implicit Euler, plain old backward Euler with a time step of 25 microseconds. And we do this with a large stimulus, very super threshold. We see the solutions are all pretty close to each other, very close to each other. In fact, the one that's a little bit off is in fact the backward Euler. The plain old implicit Euler, just a little bit off. The Crank-Nicholson methods and the implicit and the CVODE adaptive integrators produce a very nice result. Okay. But what happens if our stimulus intensity is close to threshold? Okay, just above threshold. Well, there's our stimulus. So far, all the solutions are very close together. But as we advance further in time, we'll see that one of the solutions lags behind. The other 3, the Crank-Nicholson and the adaptive integrator, are all in pretty good agreement. The implicit Euler, the plain old backward Euler, lags a bit much, and that's quite a bit of error. And if spike timing is important in your simulation, that probably wouldn't be what you want. So we can see that the integration method can be important if for things that are close to spike threshold. For anything that is close to any trajectories that come close to a separatrix. Any of you that knows dynamical analysis or nonlinear systems analysis, a separatrix is basically a locus that separates two different trajectories. One that goes one way and another one that goes the other way. They might start as a bundle of trajectories that are very close together, but as you advance the solution, they diverge more and more with time. Okay, the Lyapunov coefficient is too big. Okay. Well, okay, so implicit method isn't so great when stimuli are very close to threshold. Okay. But should we feel bad about that? Should we throw that out? Let's take a look at, let's compare the Crank-Nicholson method with a DT of 1 microsecond, which we're using as sort of the gold standard, for very superthreshold stimulation in which one run had the standard sodium conductance density, and the second run, that density was reduced by 1%. Well, those two simulations overlap very closely when the stimulus is very suprathreshold. Okay, they overlap very closely. So far so good. But what if there's even a 1% error? Again, it doesn't make much difference when the stimulus intensity is high. When the stimulus intensity is low, so that the cell is close to firing threshold, just a little bit above firing threshold, this is what we get when GNA bar is 0.12 Siemens per square centimeter, the standard value. This is what we get when it's only 1% less. Oh, and that amount of error looks very similar to what we got with when we were using implicit method with the standard Hodgkin-Huxley compared to the other integrators. Well, look at that. Close to threshold, even a little slop, a tiny amount of slop in a parameter's value becomes very important to the solution. Well, who among you has done any biophysical experiments of your own, and who among you believes that any biophysical parameter in neuroscience is known to within 1% tolerance? It ain't so. Whoa. Okay, they just aren't. They aren't known that well. Their precision on those things they're pretty sloppy. They're 5 to 10% at best. So should we really be all that excited about this error that results from using a different integrator when we can get a similarly bad error just because of parameter slop? And then let me pose you a final question. Who among you thinks that it would be a smart thing to design an organism in such a way that parameters had to be precise to within 1% or the animal might die? If this spike time is important, say, for an animal's defensive reflex to escape, to close its eye when something's heading for its eye, or to jump the heck out of the way when a foot is coming down to stomp on it, I'd like to have a robust system. I'd want to have a system where it doesn't matter if some of my cells have got slightly wrong or too much or too little sodium channel density. There's got to be robustness. Okay? There's got to be robustness in any living organism. It can't depend on critical values of parameters. Okay, so maybe that argument helps you think new thoughts about the need for precision. Are we just chasing decimal points? And what's the point of it when in a real organism, nothing's going to depend on 1% precision. Forget about it. You go out and have a good time at a party tonight, you wake up tomorrow morning, are your neurons within 1% of how they're working right now? Are you sure? And yet you can walk and talk. Oh, you might have a headache. You might feel like crap. But you're still the same person. All your systems work. Robustness in the face of slop. Okay, enough. That should get you thinking new thoughts. Any questions? All right, Robert.